So we've talked about electrophilic aromatic substitution reactions, and now we've covered coupling reactions as well. That means we know how to put 5 things on benzene dependably: carbon groups, acyl groups, sulfonic acids, nitros, and halogens. But we can also do coupling reactions to put a ton of other things on benzene. But sometimes, even if you want to put a simple group on benzene, it's helpful to be able to manipulate that group after you get it added on there. One way to manipulate that group is to do a reduction of a carbonyl group that you have on the side chain. So we could do a Friedel-Crafts acylation to get us to these reactants in all 3 of these reactions. And you can reduce that acyl group in all 3 of these reactions to yield an alkyl group. Remember, we said sometimes alkyls are a problem because those carbocations rearrange. Sometimes they're a problem because they want to alkylate multiple times and stuff like that. But if you needed to, you could do these reduction reactions in order to put an acyl group on and then add an alkyl and then end up with an alkyl group. The top one has a name of the Clemmensen reduction. The bottom one has the name of the Wolff-Kishner reduction. I don't refer to a ton of reactions by name, but sadly, these 2 I am in the habit of referring to by name. The differences in them: the Clemmensen reduction is done under acidic conditions. The Wolff-Kishner reduction is done under basic conditions. These reagents down here are on separate arrows because it's showing you one of the intermediates that it goes through, but it's a basic hydrazine and hydroxide is what's added together, all together. It's not a stepwise addition. This thing I already said is hydrazine. So zinc, mercury, HCl, Clemmensen, hydrazine and hydroxide, Wolff-Kishner. This middle one is actually a stepwise thing that you add that dicyane, the SHSH thing, dicyane, and then you add Raney nickel. Raney nickel is basically H2 and nickel, just like H2 and palladium, H2 and platinum. It's a reduction reaction, turns this dicyane thing into just carbons and hydrogens. Yeah. The middle one we will see least frequently. The top and bottom we will see a lot. So where might we use these kinds of reactions? Why might we want to do that? If your job was to synthesize something like this, the problem with trying to do a Friedel-Crafts alkylation, like so, is that the product you get is not the expected thing, because what's the electrophile in electrophilic aromatic? What's the electrophile in Friedel-Crafts alkylation? A carbocation. And carbocations rearrange. So you don't get the product that you were aiming at making if you tried to do a direct Friedel-Crafts alkylation. So instead, what you could do is a Friedel-Crafts acylation, like this, AlCl3, and then you got to add water. Water's just there to clean up everybody, make sure Lewis acid is gone. And that gets you an acyl group on your benzene, and then you can Wolff-Kishner that thing away. It doesn't matter if you chose Clemmensen or something as well, or instead, but yeah, whoops, I almost drew the wrong molecule. Yeah, there's our product. We got rid of that oxygen entirely. So those reduction reactions are useful when you can't do a direct Friedel-Crafts alkylation. But you could also make this compound up here through a coupling reaction. Do you want to do it that way? I don't know. If you want to, sure. You can turn your benzene into a bromobenzene with Br2 and fever. That's what you get when you're feeling sick, a fever. And you can add this lithium dialkyl cuprate to get the actual product that you were aiming at. But generally, if you're going to use that lithium dialkyl cuprate, you need to show how you made that lithium dialkyl cuprate, and it's going to come through something like that, where you add solid lithium, and then you add copper iodide. Yeah? The blue method, not the blue that doesn't work, but the blue method that does work is the more traditional method. The organometallic method is the newer way of doing it. I don't care how you get it done. I care that you get it done. More than COO bonds can be reduced. We can reduce our nitro into an NH2. So it's reducing because you're adding bonds to hydrogen. It's reducing because you're breaking bonds from oxygen. Reduction. We don't know how to add an NH2 directly to the ring, and in fact, our coupling reactions also don't tell us how to add an NH2 directly to the ring. The only way to get an NH2 on a benzene is to add it as a nitro and then reduce it. So if we add iron and HCl to this nitro, it will do a reduction, but there's a second step that's missing. HCl is hydrochloric acid, and the first thing you learned about amines is that they are bases. So after step number 1, you don't have aniline. That's what that thing is, that product. You have anilinium. You have a positive. So we have to add some sort of base to make sure that that thing gets neutralized and we get a neutral amine rather than an ammonium. Yep. You could also use tin and HCl, but it's got the same issue that it's acid. You got to make sure that you neutralize with base. This middle reagent is called lithium, aluminum hydride. It's known as a hydride donor. We will see it do tons of reactions in the very near future, but one of the reactions it could do is reducing a nitro. It is a basic thing already. Remember, hydride is a pretty strong base. It's up there next to an N-. Pretty strong base, so you don't need to add stuff besides lithium aluminum hydride. You could also do H2 and palladium to reduce a nitro. Be careful, different conditions reduce different functional groups. These things, zinc, mercury, and HCl reduce a COO, but zinc, mercury, HCl, not so good at a nitro. Hydrazine and hydroxide reduces a COO, not so good at reducing a nitro. Same thing in reverse. These groups are good at reducing nitro, not so good at reducing a COO. That's reduction. What about oxidation? Uh-oh. This is a delta that didn't show up. Lovely. So this is oxidation. We've seen KMNO4 before. It was an oxidation reaction then. This is KMNO4 with base. Kind of important that it's with base. It's also heated. That heat tries to indicate to you that this is called a vigorous oxidation. KMNO4 is a very strong oxidizing agent. So is chromium. So you could use KMNO4 or chromium to oxidize the side chains. Remember, that's why we're headed down this path. You only really know how to put 5 things on through electrophilic aromatic substitution, and you can widen those possibilities with coupling reactions, but still, sometimes you need to do other manipulations to the side chain so you can do an oxidation. This, to me, is called the Pac-Man reaction because it says, and it chews down carbons all the way to the benzylic position, and it makes a benzylic radical. The mechanism we're not going to walk through, but it makes a benzylic radical, and then that gets oxidized. That benzylic carbon becomes oxidized. that benzylic carbon becomes a carboxylate after step 1, and then you add some acid in step 2 to make sure that you get a neutral carboxylic acid in the end. Yeah? You completely destroyed these 2 carbons. You lost them. They're off into the oblivion. You don't care what happened to them. You made benzoic acid out of it. So KMnO4 is basic KMnO4. Chromium stuff, remember CrO3 with acid was one of the things we saw. You need to heat it for it to be vigorous oxidation. Chromic acid itself was acid. You need to heat it to make sure it's vigorous oxidation. Sodium dichromate, potassium dichromate with acid. You need to heat it to make sure it's vigorous oxidation. So we can do acidic chromium. The difference between KMnO4 and chromium, acid versus base, follow up with acid to make sure you have a neutral compound in the end, versus it comes along with acid and creates a neutral compound from the get-go. Yeah. So lots of side chain things can be oxidized. The only thing is you cannot oxidize a tertiary side chain. This benzylic carbon can make a radical even though it's an alkene. Yeah. This benzylic carbon can make a radical even though it's an alkene. So can this one, but this one, no go. That one is not oxidizable through this vigorous oxidation reaction. So that one stays the same, while all these others become carboxylic acids. It's a little bit of a crazy example to have this many functional groups, this many carboxylic acids all around, but the point is you can oxidize a lot of different groups around there. Like alkyl groups, except tertiary alkyl groups. Like alcohols, if we had had something like a primary alcohol out there, yep, you oxidize that thing to become a carboxylic acid, for sure. COO, if we had an acyl group out there, like this, yep, that oxidizes to a carboxylic acid. That carbon just disappears. Alkenes and alkynes, So that's oxidation and reduction of the side chains. Can you do other reactions to the side chains? Of course you can. Br2 and light, what kind of reactive intermediate does that go through? Anybody? Anybody? It goes through a radical intermediate, and the most stable radical will be made from abstracting a hydrogen from the benzylic position. So you abstract a hydrogen from that benzylic spot, you get a benzylic radical, and then the bromine gets added in place of that benzylic radical. Now that you have an alkyl halide, you can do a ton of things with alkyl halides, like SN1, SN2, E1, E2. It's a benzylic alkyl halide. Carbocations are pretty good. You can do substitution because it's a secondary alkyl halide. Yeah, you can do a lot of things with alkyl halides. Sometimes you need to manipulate your side chain after you've added stuff to the benzene. You can also add NBS with peroxide. That does allylic/benzylic bromination specifically. Remember, NBS is N-bromosuccinimide. That's this guy. N-bromosuccinimide, NBS. That's a specialty reagent that does allylic benzylic bromination only. Alright. So yep, I said once you have a benzylic bromide, a benzylic alkyl halide, you can do a lot of things with it. This is a primary benzylic alkyl halide. Primary says SAN2 most of the time. When it's benzylic, sometimes you might make exceptions, but cyanide is a negative anionic nucleophile. It's not going to be an exception. We're going to do some SAN2, like that. This stuff down here is all neutral. There's nothing anionic here. This one did SN2 because we had anionic. This one can make a pretty stable carbocation. Yes, it's primary, but it's benzylic. And this one I would expect to actually go through SN1. Diva leaves behind the carbocation. And then this guy attacks. And then something comes to clean up. And you end up with that ester. So, we've said we can do some reactions multiple ways. Remember back yonder when we synthesized this compound? We did it a purple way and a blue way using Friedel-Crafts acylation then reduction, a purple way using a coupling reaction with a Gilman, a coupling reaction with a lithium dialkyl cuprate. Yeah, it's often good to have more than one way to do a reaction. The reason being, especially in examples like this, when you have a bifunctional molecule, you want to make sure that both functional groups react if you want them to, or you want to make sure that one functional group reacts while the other one doesn't if you want that instead. With lean-mean hydrazine and hydroxide, does that do anything to alcohols? Nope. It only reduces the ketone, the carbonyl. Oh, I'm tired, guys. This is the Clemmensen reduction. We've got HCl as part of the Clemmensen reduction. Does HCl react with alcohols? Yeah. So you can turn that alcohol into an alkyl halide and simultaneously reduce the carbonyl if you use Clemmensen. If you use Wolff-Kishner, the alcohol stays the same and the carbonyl goes away. In this example, hydrazine and hydroxide, that does not bother the nitro group. Nitro stays the same, but the ketone gets reduced. H2 and palladium over here reduces your nitro group, but simultaneously reduces your carbonyl as well. I'm not sure if I said that wrong before. H2 and palladium can reduce benzylic carbonyls. Yeah, okay. So this super vague title, what are we trying to do here? What I want to say on this slide is, have we learned how to directly connect something like a cyanide to benzene, a CH2 cyanide directly to benzene? No. Have we learned how to directly connect something like this to benzene? Only through a coupling reaction. Hold on. Have we learned how to connect something like this to benzene? No. Have we learned how to connect something like even a carboxylic acid to benzene, or an ester to benzene, like that? No, we haven't. If our goal was synthesize each of these molecules starting with benzene, how the heck would we do that? Well, let's walk through a little bit. If we're going to try to make that first one, we're going to need a carbon group on benzene. Maybe we add CH3Cl, AlCl3. We get a CH3 on the benzene. What good does that do me? Well, I can do some NDS and peroxide to do radical halogenation of my benzylic carbon to give me a Br. And now that I've got a benzylic bromine, I can do some cyanide SN2 displacement. Like so. Is that how you would have put it together? I don't know. Maybe so, maybe no. I don't know. How about another one? Which one do we want to do next? Let's make this ester. Sure. Ester. If we're trying to make this guy from benzene, how the heck do we do that? Well, we could add on a carbon group. I don't know, a couple of carbons. Like that. And then we could chew some of them away to make a carboxylic acid, because we've learned a carboxylic acid plus alcohol plus extra acid yields an ester. Yeah. So based on the few reactions, the 5 reactions of putting things on benzene, plus coupling reactions, based on those few reactions, we can do a ton of stuff on benzene side chains because we have this whole wealth of knowledge of all the other things we've studied. So it gets pretty overwhelming if we're not super up to date on all that old stuff. You should brush up on it. Coming up next is, what if I've got one group on benzene? What if I want to put a second group on benzene? How do I do that? It'll be a challenge, but it's good. It's got good patterns. I think you'll like it.